बोल सकते हैं, पूछते हैं उसको क्या वो लोग प्लान कर रही है। हाँ, लेकिन उसका छुट्टी होना चाहिए ना संडे को। रश्मि का सन-
Hi,
Good morning, sir.
good morning.
Uh, Good morning, everyone. Welcome to today's faculty development program on application of artificial intelligence in chemical engineering. It is privileged to introduce Dr. Vishwanath Dalvi, faculty member of ICT Mumbai, an institution that believes fundamentals are scared and shortcuts are suspicious. Dr. Darvi works lives at an interesting intersection. On one hand, he is deeply rooted in decentralized grounded technologies such as solar thermal heat and power, biogas from agriculture waste, waterless sanitation system, and open source process simulators. On the other hand, he looks unapologetically forward, asking how modern tools like AI can accelerate process development and simulation without diluting engineering judgment. His guiding philosophy is repression honest. Prosperity in India must rise from the bottom of the pyramid. Academically, his journey reads like a word map of chemical engineering excellence. A bachelor degree from ICT Mumbai, a master's from the University of Twente in the Netherlands, and PhD from the University of Texas at Austin, USA. He joined ICT in 2010, and since he has built reputation not just as a researcher but as an exceptional teacher, earning teaching awards from both ICT Mumbai and AICT. Let's be real, good teaching in hard is harder than good publishing. Today's session titled AI for Rapid Process Development and Simulation. We warmly welcome Dr. Vishwanath Dalvi and look forward to an insightful session. Welcome, sir. Now we can start your presentation. Welcome, sir.
Thank you so much, madam. That was a very, very kind introduction indeed. I'm very thankful to you.
It's my
Um,
pleasure, sir.
so what we'll do is, I was told that we want to make something hands-on here. So I don't know if you can follow along, but I'll do something a bit um, non-conventional. I'm not going to present a PowerPoint. I'm is instead going to present an Excel sheet or a number of Excel sheets, and we are going to look at a important problem in chemical engineering, especially for the pharma processing group. So basically a fed batch reactor. So um, what I would like to do is take you through the sheet and introduce you to what I think is an incredibly clever algorithm for dealing with problems of really great industrial interest. The algorithm is, so let me share screen first. Now this is well, this is a demonstration, and it is an Excel. So it is designed to repeat the same thing over and over again, so that we get the idea, we get that point reinforced in our minds. But if you have any doubt, please feel free to interrupt at any time. Also, madam, please call me in case the internet drops. I have a pretty stable line here, but in case for whatever reason the line drops, I will not know because I'll be fairly deeply into the demonstration. So please give me a call, and I will, if it does drop, I will back up to where we were interrupted and carry on from there. So interrupt whenever you like, and if I drop off, please let me know. Otherwise, I'll be talking to myself for several minutes. So let's begin with some data. Uh, this is a problem which is very commonly encountered in process development. What we have is a reactant, say A and B, and the reactant A is taken inside a stirred tank, and it is heated to the reaction temperature, and reactant B is added semi-batch wise, fed batch wise. What it means, of course, is that the volume of the reacting mass increases with time, which of course also means that the reactants are diluted as a function of time. But they're not just diluted, they're also reacting. So there is a catalyst whose concentration, initial concentration, we know. Of course, as we add reactant B, the concentration will keep going down. And what we do is every so often, every 10 minutes or so, we take out an aliquot of the solution and we run it through some analytical method, GCHPLC or such. And we find out the concentrations of some of the species that exist in the pot. Not necessarily all, just some. So here is some raw data. We have some information. Initial volume in the reactor is 100 ml. Initial concentration of reactant A is 1 molar. Initial concentration of the catalyst is 0.1 molar. Initial concentration of B is 1 molar again. Initial feed rate of B is 1 ml per minute. And the concentration of B in the feed is 1 molar also. So this is the setup. Several of you will have encountered this setup through your careers. It is a very, very common setup. And the problem, of course, is you get these nice time profiles. So CA drops, CE increases, CG increases like here, and CB remains. CB is consumed very quickly, and therefore its concentration does not rise very much, but it is there. Now we would like to fit this to a kinetic model, a typical exercise in reaction engineering. So the very simplest way of doing it, which is what a lot of people do, is you postulate a reaction mechanism. You postulate it and you write a model for that reaction mechanism, and you use non-linear least squares to fit the parameters of that model so that the fitted simulated profiles match the experimental time profiles as closely as possible in the least squares sense, which is standard, which is there is a, and this can happen routinely. This happens on a regular basis. It's not anything new. But this is still human intelligence applied to with straightforward differential equation solution and optimization tools. Pretty old. So we have lovely tools now like Python that can do this. But what would be really interesting? What would be really interesting is if we could get the mechanism or get a mechanism, get a plausible mechanism without taxing our intuition too much. What would be interesting is, and this is actually the heart of what is meant by machine learning. Why do we call it machine learning? It is because we expect the machine to figure out by itself automatically what we would spend many hours doing. So this is not trivial. This is not trivial. So the what I'm going to present now is the results of ideas which are available in this seminal paper by Stephen Brunton, Proctor and Kutz, and it is called hello. Sorry. So it is called sparse identification of if you, I am a bit confused. Are you? Do you want to say something? Or do you not? That's good. Oh, you're talking on the phone to somebody else. All right, sorry. Let us continue. Discovering governing equations from by sparse identification of nonlinear dynamical systems, and they have given this a lovely name, which is sparse. So that's SINDY, SINDY, SINDY. So that is now that what is very exciting about this is you can extract insights from data without doing too much thought work yourself. But you have to do a little bit of pre-processing of the data. So let's look at the idea behind Cindy very quickly. The idea behind Cindy is like so. If you have data, the X, Y, Z here, and you have the derivatives, time derivatives of the dependent variables, okay, the time derivatives of dependent variables and the dependent variables, then it might be possible to convert this problem into one of ordinary least squares regression. And it's an ordinary least squares regression problem with the additional constraint that the coefficient matrix is sparse. So let's look at what we have. We have for every time step or every entry, as it were, the derivatives x, y, z, and a library of functions. So this is why this phi matrix is also called the library matrix. So you have a library of functions. So you can have the constant, you can have x, y, z, x squared, x, y, x, x, y squared, y, z, z raised to 5 and so on and so forth. So you can have sine x, cos x, e raised to x, whatever function you think would be applicable. And if you have some domain knowledge of the system, it's very helpful to make the phi matrix smaller. The smaller phi matrix converges more robustly. And then for every one of these functions, there is a coefficient. And those coefficients live here in the coefficient matrix. So you can see this is the n by 3 derivative vector or matrix. This is a m by n matrix, and where m is the number of functions in the library. Every function is the coefficient. So this is the m by 3 coefficient matrix. So if you multiply this, you get a matrix which is n by 3, like this one. The key here is we are going to solve. We could just to get the coefficient matrix, we could simply solve this set of equations. But that's not what we want to do. Get to the check. We want to solve it sparsely. That is, we would like most of the coefficients to be 0. And we want the small subset of coefficients to be non-zero. But we still recover or still fit the dynamics in a sufficiently robust way. So now we are going to look at what all of this means. We are going to actually build these matrices and solve them. And because this is a workshop, we are not going to do it in Python. We are going to do it. Most of what we are going to do is going to happen in Excel. So let's get on with it. So we start with the raw data. The raw data that comes from the analytical chemist team can be written in this clean form. At time, there's a timestamp here, and then there are the concentrations. And then you know how the process development team carried out that experiment. So these things are known. So you get time profiles of concentrations. Now, since the volume is changing with time, it is not a good idea to write derivatives in terms of concentration, because the concentrations are a product, are a composite of moles and volume, both of which are functions of time. So we should convert everything to absolute moles. So we have done that here. So we know the rate at which volume enters the system. This is our data as it is. We know the volume of the system at any point of time. This is the initial volume. And then after 600 seconds, the volume will be flow rate into 600. So we have that many flow rates. So at the end of the thing, the volume has effectively doubled. So the increase in volume is not negligible. It has to be explicitly accounted for. And therefore, we, instead of doing our dynamics in terms of concentrations, we will do our dynamics in terms of moles. So once you have volumes for everything and you have concentrations, getting the moles is very easy. You multiply the volume by the concentration, you have the moles. Multiply the volume by the concentration, you have the moles. So here you have the moles of the system. And they look like this. They don't look very different from concentration, but they are different enough. Okay, so this is what we get. Um, how do we get the derivative? It is this is the part that really kills um, endeavors like the one we are going through. Because getting derivatives is very fraught with noise. So why don't we say just do a forward difference? Why don't we just do a forward difference? So let's do a forward difference. Let us do a forward difference. So I'm going to write dNA by dt, and I'm going to get k moles per second, and I'm going to do it by a simple difference method. So it is Na minus this on P minus P. All right. Notice that we have, if you look very closely, you will see we have a problem in our hands. You can see that A is unquestionably decreasing with time. And this jitter here is due to experimental noise. It is due to experimental noise. But if we were to plot the derivative as a function of time, let's give it a this would be the derivative. There are places where the A actually appears to be increasing. It's a it is this curve is so not just jagged. The curve is no way of telling straightforwardly what this curve is even. It is so incredibly noisy. For example, you can take uh, let's say I have the mean, average of this curve, and I have the standard dev. And let me percent. So let's see, I do standard deviation upon mean into 100, and I get 90%. This is, for all practical purposes, this is a useless curve. It is so noisy that you cannot get a trend out of it. It is incredibly noisy. So what do we do? How do we denoise this curve? Uh, some of you might have had uh, experiments in which you have a curve like this. So one way what people do is they fit this curve um, to a poly, polynomial, and and so actually this curve fits really well to a polynomial. But let's illustrate with this one. We fit this curve to a polynomial, and we try to see how it. So this is one way of smoothing it. The the So I suppose these illustrations are not the very best to illustrate what I'm going to motivate what I'm going to say. But if you fit this curve to a polynomial, you are generally going to get jitters, especially when this curve stabilizes up here. The polynomial goes up and down. So when the derivative is zero, you still get, when derivative has to be zero, you still get waves. So you want a robust way of differentiating. So getting finite differences is not really a very good way of doing it. Um, Polynomial is better than finite differences, but if for any reason your curve stabilizes, like you do it at a very long period of time, that polynomial is going to wave like anything. So that's not the very best way of doing it. What do I mean by wave like anything? Let me show you one example. So I have time and I have c, and time is 0 and c is a simple 1 upon 1 1 plus exp minus t type of curve. So okay, so this is a just shown you a Pare approximate. Insert pretty straight. Let's have some more. Now we have this curve. Let us try and fit it. Let's see what the derivative would be. dc by dt would be minus 1 upon, so it will be c squared into exp minus t, which would be c squared into exp minus. Okay, let's now fit to a C polyfit. Just fit it to a polynomial at trend line. Polynomial. And let's make it so you can see the polynomial is going like this, but let us make it a order 4 polynomial. And we will, of course, ask for the equation on the curve. And we'll also ask for okay, we'll do that later. Mm. So C fits really well, but what would the derivative look like? Let's So this is the data, and this is the fit. So it fits well, but it does something really strange over here. It rises when our actual fit is dropping. And if you had extended it further, this would have got worse. So let me just quickly illustrate. Mm. But yeah, it would be you have to refit it and so on. But you see that if you go further, this derivative is going to oscillate. So it's going to be very troublesome to fit it to a polynomial, especially if you have stabilizing sort of things. Instead, we can get derivatives by a new method called total variational differentiation. And total variational differentiation tells us that for any data that we have, we will find the derivatives using an optimization algorithm, which does two things. First thing it does is it reproduces the data in an Euler fashion. So y0 at I is j1 to I uj delta t. This is simple Euler integration. Simple Euler integration. It reproduces data by Euler integration, like so. So that the sum square error is this, and it wants to, you choose UJs to minimize the sum square error. And that would, if you did only that, you would get a very noisy, you would get the same result as the finite difference thing would give you, because this is effectively finite difference. But you don't do that. What you do instead is you add an additional constraint and the additional constraint is that the subsequent derivatives. So derivative of time step k plus 1 minus derivative of time step k should be less than the absolute value should be less than a threshold, say lambda. So when now you have to write the code in Python, but you can get a gradient in. So the sum squared errors of the residual are this. So if you take the partial of the sum squared errors with the derivative at time step k, it only affects yi calc from here. So this is effectively the partial, the residuals appear here and y calc over here. So then you have this as the derivative of your, this has the sensitivity of SSE with respect to UK. And then you can just do a conjugate gradient optimization. Keeping in mind that at every step, if UK plus 1 minus UK exceeds lambda, then UK plus 1 is clipped so that the difference remains less than lambda. So you do a conjugate gradient, but at every update, you make sure the difference is less than this. When you do that, the code in Python looks like this, but this is widely available. If you just ask for total variational differentiation, ChatGPT will write you the code. So that is not the big deal. So what we are doing here is this thing smooth derivative function, which is over here. It it makes sure that the difference in derivatives, which is this p, is clipped between a threshold so that it is always smooth. And so you smooth the derivative first, then you get the gradient, which is essentially these terms, and then you do a conjugate gradient optimization. After several iterations, you get a converged value of your u and your y calc, and you return them. So the result of that appears over here. So this is the derivative. This is the smooth derivative of A, and this is of NE. And you'll notice that the derivative is not the it works through these noisy points and gives you what you need to work with further. So here you have the derivatives. So now that we have the derivatives and we have the functions, we can build a library matrix, and we can set up these matrices and then solve the coefficient matrix. So let's go down to it. Before we go there, we have to scale appropriately. Just a quick look at these derivatives tells us that they are extremely small. So when things are so small, machine precision becomes a major issue. It would be good if these were something of the order of 1 to 100 instead of 10 raised to minus 8. If they were of the order of 1 to 100, maybe 0.1 to 100, in that range, then we don't have to worry about machine precision. So what we'll do is, these are kilomoles per second. We will express them as moles and moles per second, and volume we will express in terms of liters, just to make everything come close to unity as much as possible. There is one other thing. You will notice that NB is increasing with time, but NB we know is a feed. So what we should do, there is a part of this gradient of NB which we know exactly, and that is simply flow rate into CB naught. So we'll just remove flow rate into CB naught in moles per second from the derivative of NB, and now we get a nice negative. NB is now, like everybody else, all reactants, decreasing with time. So Na decreases with time, Nb decreases with time, Ne increases with time, and so does Ng increase with time. So they are both, two of them are decreasing, two of them are increasing, and there is a problem with systems like this, which are catalytic, in that this is actually one of the reasons we are doing this exercise. We really don't know what the intermediate species are. It would be good if we knew that. It would be good if we knew what the intermediate species were. But there's no way of finding them. We don't have the tools normally. GC, by the time the product goes for a GC or an HPLC, the reaction is quenched and the intermediate species have been destroyed. So if there was some complex with the catalyst by A or B, or maybe E or G or whatever, if there's a complex with the catalyst, it would not survive the workup. It would go back to A, B, E, or G. So we have to introduce what are called latent variables. We will get to them soon, but we'll just postulate that there are two other variables, we don't know what, which which are hidden. So we have the apparent variables, which is the addition, the rate of change of volume, or the inverse volume, the inverse 1 upon V is Q. The moles of A, B, E, G, and N, C, and we have the two latent variables. Now we are two latent variables. Now we are in a position to write out a library matrix. So what would the library matrix be? dNA by dt could be a function of just Ca. That is why we have dNA by dt is V into Na upon V. V when cancels out, you get Na, Nb, Ne, Ng, Z1 and Z2. Then there are the product terms, Ca square. So this is V into Ca square is V into Na square upon V square, which is Na square upon V, which is Na into Q. Similarly, Na into Ca into Cc, Ca into Cb, Ca into Ce, Ca into Cg, Ca into Z1, Ca into Z2, B Cb square, Cb Cc, CBCE, CBCG, CBCZ1, CBCZ2, CECE, CENC, CENG, CZ1, CZ2, and you keep going this way with the self terms of Z1 and Z2 as well, and you end up with something like 33 variables, 33 columns in your library matrix. So we now set up the matrix problem. These are our inputs. Right now, the latent variables are see, we have said no latent. So the latent variables are set to 0. So they will not be seen. We have a library matrix in its original unit. So it is unnormalized. It is unnormalized, which is a bad thing, which is a very bad thing. Why is it a bad thing? Because if it's unnormalized, we can't compare the coefficients on an equal footing. If it were normalized, the coefficients could be compared on an equal footing. So if it's unnormalized, the coefficient would be a function of the magnitude of this term. So if in the beginning, QNA square would be way, way bigger than QNE square. And therefore, the magnitude of coefficient of QNA square would be smaller than the coefficient of QNE square. And there's no way of saying whether that difference in magnitude of the constant is because of something inherent about the constant, or just because it's multiplying a small or large term. So we have to normalize this matrix. What do we normalize with normally? So the very best thing to normalize with, people say, is the vector L2 nod. What does it mean? You take the dot product of this vector with itself and take the square root of that. Let's see what it looks like. So it's square root of m mult of this vector with itself, and you take the square root of that number. So it doesn't matter if it's positive or negative or whatever. It just positive, so it doesn't matter. So you have a very good L2 norm. And what you do next is you divide each term with its L2 norm, and just for fun, you add a small term in front of it in case this L2 norm happens to be zero, like it happened, like over here. So instead of getting a div zero error, you get a number which is just zero. So this is your library matrix normalized. Normalization of the library matrix is the same as multiplying your unnormalized library matrix by the diagonal matrix of inverse norms. That is, you take a matrix whose norm, whose diagonal value is the inverse of this number here. So it is what we are doing here is exactly the same as multiplying it by the diagonal matrix. So it's the same thing. So you multiply this by this, you get this matrix. But we need this diagonal matrix. It's a 33 by 33 matrix. We need this diagonal matrix later on. In fact, immediately right now. So here is the coefficient matrix with a normalized library matrix. This one. So you have A, B, C, A, B, E, and G. These are the coefficients corresponding to A, B, dNA by dt, dNB by dt, dNC by dt, dNG by dt. You have A, B, E, and G, and the coefficients are currently all zero. This is an activation matrix which we will bring in later. In the activation matrix, if a term is 1, then that coefficient is active. If this term is 0, that coefficient is 0. An activation matrix is also called a mask. So what you do is in order to get recalculated values of dNA by dt and so on, you would multiply the coefficient matrix. You would multiply the library matrix, which is this one. You would multiply the normalized library matrix, this rectangular matrix, with the element-wise product of the coefficient matrix and the mask. So because every term in the mask is 1, this is the same as multiplying this matrix with this matrix. And you get the derivatives from that. This is the result of the matrix multiplication. And once you have the results from that, you can calculate dNA by dt is 0 in this case. But dNA by dt at time t equal to 0 is known. So we can subtract the two and square the error, and you get 148. You can do it for all of these, and then you add. So you sum all these squares, so you get a sum of square errors. And so we have set up the problem. So this normalized matrix multiplies this. So we have set up the problem. Once we solve this problem, you will get coefficients in for the scaled variables. Once you solve this problem, you're going to get coefficients for the scaled variables. To get the coefficients for the unscaled, so the unscaled coefficient matrix is this matrix multiplied by the this matrix, and that you get over here. So these are the unscaled values or the result of the unnormalized values. So these are the physically relevant parameters. The first thing we do is we would like to solve the dense matrix, which means we keep all the coefficients active. We keep all the coefficients active, and then we go to, you can do it in Python as well, but here we have solver. So we're going to go to solver. We set the sum squared errors to be minimum by changing all of these points. So there's a lot of points. So you set up the problem, and because I have already solved it, it should not take very much time, but you can see, monitor the progress of your simulation over here. Well, let me interrupt this because it's not going to go very much farther from that. So these are the values of the coefficient that minimize the sum squared error between the recalculated derivatives and our original derivatives. So this is the matrix. Now let's look at the coefficients. So this A has coefficients in 19 and 13, but it also has coefficients like 4 and 2. Look here, 20, 30, 39, 14, also coefficients 6 and 8. So maybe 1.2. So there are a lot of coefficients here that can be set to 0 without much loss of fidelity. So we will do that in our first thresholding. In our first thresholding, we will say that the maximum value of any column here, we will take that value and we'll say anything less than 50% of this in absolute terms is going to be set to 0. So when you do that thresholding, so 50% of 39 is 19.8. So when you do that thresholding, you see most of the parameters drop out. So we have said if ABS of this of if ABS of absolute value of this number is greater than the threshold, that number stays. Otherwise, it's set to 0. So this is, it stays, it doesn't stay, it doesn't stay, stays. So only the terms that are contributing significantly to the model are retained, and everyone else is thrown away, is set to 0. Now, so we have a much smaller set of coefficients. Before we had, how many did we have? We had a very large number of coefficients. Before we had 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 into 4. So we had 72 parameters. Once we threshold, number of parameters drops to 16, which is a great improvement. So this dense matrix, the SSE was 1.2. Now, what would be the SSE of this sparse matrix? You see how this is sparse? Most of the terms are 0, except very few that are 1. Now, of course, since we have a new sparse matrix, it behooves us to refit it. It behooves us to refit it. So what you do in the refit is you set all these terms to 0. You produce this by multiplying the library matrix with the product, with the element-wise product of the coefficient matrix and the activation matrix. The coefficient matrix and the activation matrix. One implies the coefficient is active, the other it does not. So only those coefficients where the mask is 1 will contribute to dNA by dt, dNB by dt, or so on. So let's check out what's going on in the lab. Okay, let's solve. It's dropping quickly. So yeah. So you will see that only the only the coefficients that had a non-zero mask have been fitted. Now you'll also see that there are some large numbers and there are some reasonably small numbers. So we can probably do a second thresholding where the number of parameters probably is more important than the fit of the derivative. So now we refit after the second thresholding, and when we do that, nothing happens. So we are now as good as we are ever going to be, and we can now look for the actual coefficient of this in the unscaled coefficient matrix. So this is the unscaled coefficient matrix. How did we get this? We multiplied the diagonal matrix with this matrix. So we got the unscaled coefficient matrix. And then you can write every term in the unscaled coefficient matrix has a meaning. So let's quickly write the meaning. Just paste like so. So dNA by dt is minus 659 into Na plus 5751 into CACC. And we have multiplied everything by all the derivatives have been multiplied by 10 raised to 6 to keep the to save ourselves from numerical precision errors. Then there are only two parameters here. For B, we have minus 744 into CA and this into CACC. For E, we have CACC here plus CCCC here. And for G, we have minus 3452 CACG plus 18.11 CECC. Now you will notice that this, although you'll notice first that it is a small model. It's a small model. It has identified the most important parameters here and is showing it to us. But although it is a small model, it is in many ways not correct. For example, we know that A only decreases. And therefore, this term is not physically plausible. This is the feed term for B, but there is no term here that says that B decreases in a manner proportional to B. So it as far as B is concerned, the reaction is of zero order. Again, E is being produced here at a rate proportional to E. So we don't know what to make of this. This does not seem to be standard because E should be, if anything, the higher the E, the more it should degrade, if anything. But here also, G is decreasing at a rate proportional to G, which is fine. So this looks okay. But we are really flummoxed by this term and this positive term. Why is A being produced in the system? So we have got so far with a very naive approach. We have got so far with a very naive approach. Why naive approach? Because we did not add any of our insights into which of these parameters are very likely. So generally in chemical reaction engineering, we have this idea of mass action, which means two molecules, in order to react, they have to collide. A molecule does not spontaneously decay into another molecule. It either goes through a catalytic, either combines with the catalyst first, or collides with another molecule, or does something before it can degrade. So we would like our reaction mechanism to be written in terms of elementary reactions, in which there is one reactant one, in which there are two reactants and some products. So let us incorporate let us incorporate the idea of mass action into our model. So we start like before. We have the raw data, which we are converted to moles. We have just taken the same value. We have got their derivatives. We scaled appropriately. We got the latent variables, which are right now 0, no latent variables. We set up the matrix problem, and let's look at the matrix problem that we have set up. So let's look at the matrix problem that we have set up. First thing we have done is all these unitary terms, these first order reaction terms, we have suppressed. We have set them all to 0. Similarly, we don't have any latent variables right now that are all 0. So we only have the mass action terms, NaNA, NaNC, NaNB, NaNe, NaNg. So these are the only terms that are active right now. So we set up the problem again in terms of normalized library matrix as one below, and set up the problem again and solve the dense matrix. So every coefficient is in play right now. We solve the dense matrix and we get this result. Solving the dense matrix is very, very easy. You just go to data, solver. Say you want to minimize SSE over here. So we are going to minimize the sum squared error by changing all the parameters in this matrix. Now, some parameters will make a big difference if changed. Others will be multiplied by 0 and they won't make a big difference. So it's already converged. We won't waste time converging this. So we have this coefficient matrix. Now let's take a look at this coefficient matrix. You have 28, 54, 8, 4, 6, so 0.8. This can very quickly go to 0, 2. So we'll first threshold this. What are we saying? We find the maximum. Anything less than 40% of the maximum is going to be excluded. So when we do that, you find the matrix becomes very sparse. And now that it becomes very sparse, the coefficients corresponding to these cells over there have to be refit to make them appropriate for this new model. So you have a very small number of coefficients in this. So this is a very, very sparse matrix. And now we want to minimize this with using these. And it's not going to go very far. Let's just not, it's already converged, so we'll just stop and say okay. So this is the matrix. This is the matrix. This is the sparse matrix that we have got. But we can threshold it further. It still has a certain number of parameters. So we can threshold it so that each column has only two non-sparse, non-zero elements. So we have thresholded it so that each column has only two non-zero elements, which means, and then we have to refit this matrix with this new thresholding, which we have done. And we get unscaled coefficient matrix. So the model now is dNA by dt is minus 120 Cs squared minus 3752 CECC. So this is actually physically very, very sound. If Ca is going to decrease, there might be a decay. This is not so sound. One would have expected Ca to feature here, but instead there is Ce, this one. NB again does not see, NB does not see B at all. dNB by dt should be substantially governed by the concentration of B, but we don't see that. dNE by dt, this part makes sense, this part does not make any sense. And dNG by dt, they both kind of make sense, but there are some unphysical terms here. So let's try some other, but you notice how cool it is that we are using just Excel. We have set this entire problem up using only Excel, and the system gives us a model, a reaction scheme that is plausible. We only know that this doesn't work because we know something more. We only know it doesn't work because we know something more about the system. If this were an unknown system, we would have no trouble accepting this model, because this is a sparse identification of nonlinear dynamics. So this model would have been fine for us. But we know that this is a catalytic system. So there are latent species which we cannot see from our analytical experiments, and which we would like to look at. So the latents as well, we are now going to set the latents to a small positive number in case they are in case they feature anything. So our mass action variable, we are not going to use the constants. We are going to use only the mass action variables. Unfortunately, here, let me just take the next, because we are nearing the end of our time. Let me end strongly with a drop of we got the latent variables, which we got them here. We have set the latent variables to 0.05. So we have Z1 and Z2 in their form. They are some kind of catalytic complex. That is why we have them. We have set some parameters which we know will not react. So A will not react with E, A will not react with G, NB will not react with itself, NB won't react with NE or NG directly, NE won't react with itself, NE and NG won't react, NG and NG won't react. And then these catalytic complexes will not further react with themselves or with the catalyst. This is a domain knowledge that we have imposed on the system. So with that imposition, we can set up the library matrix, normalize it, use the normalized matrix and the coefficient matrix with the normalized library to recalculate the uh, derivatives. So there is one thing now that we have to do, which we did not do before. Here, we are not just going to optimize the coefficient matrix. We are also going to optimize the values of Z1 and Z2. But we are going to optimize the values of Z1 and Z2 in such a way that the derivatives are smooth, or the variance in the derivatives is minimized. So our objective function becomes the sum squared error plus lambda times the sum of the variances of the derivatives of Z1 and Z2. So it's a compound objective function. And when we solve for it, we get a set of 96 parameters, and the value of the objective function is 14.5. So 96 parameters is essentially you're fitting noise. That's what you're doing. 96 parameters is too many. So let's threshold this. Let us threshold this with 20%. So now the number of parameters becomes 30. Instead of 96, we have 30 parameters. So we refit these 30 parameters. We have the activation matrix, we only refit the 30 parameters, and we refit the Z so that the latent variations are minimized. And then with 30 parameters, we see that the system is actually improved. The objective function is actually lesser with fewer parameters, which indicates the system is more robust. So this is good news. So let's do a second thresholding. The second thresholding, we now have 13 parameters, which we will refit. 13 parameters, which we will refit. And when we are refitted them, you will see that when you go from 30 to 13, when you halve the number of parameters, the objective function increases by a very small amount, few percent. So really, we have not, a lot of these variables were pretty superfluous. So let's do a third threshold. Now we have only 9 parameters. So if you refit, including the z's, and you have 9 parameters, you see that the objective function has increased by another few percent. So if you plot the objective function value as a function of number of parameters, you will see that it drops up to a particular value and then remains constant. So really, 9 parameters is plenty. Is plenty small. It's small enough, spread over 4 variables. So it's about 2 variables per parameter, two parameters per variable. So you can write the model. So let's look at how we write the model. 1 upon V dNA by dt into this scaling factor is equal to, what is this? Corresponding to QNANC, which means CACC. So this is 1359 CACC plus 49517 CBCC minus 2431 CECC minus 24,776 CGCC. So this is good. These 3 are surprising. There is really no reason for this. If you go to B and you do the same thing, you go to B, you have this is the addition term, and then you have one six seven nine CACC, and you go down here and you get CECC minus 3592. So something is added and these two things subtract, but you notice that B does not appear in its own thing. So what and then there's the NE, which is CACC and CECC. Here also on physical, NE, CE, NE is almost always change in a parameter is negatively correlated to its concentration. Here it is positively correlated. So it's not the best model. It is not the best model, but the important thing is we know it is not the best model. I mean, that is, it has reduced a large number of parameters in the library to a small number. So it keeps telling us what are the parameters which are important and which keep recurring. We will try one more time to see whether we can impose some of our, whether we can prune some more parameters. that CCC appears to be very troublesome. So why don't we get rid of that? We will try and we'll try to set up the problem such that the CCC term is just eliminated, but the NBZ1 terms remain. So, but CCC term is eliminated. Now, when we do that and we go for the dense matrix, we have only 44 parameters. Most of the parameters just drop off. We have deliberately made the problem simpler. We have 44 parameters giving us an objective function of 14. And then we threshold it. And when we threshold it, we get (32 parameters. So that when we refit it after the first thresholding, we still get 14 parameters. So we threshold it further. And now we have 18 parameters. But when we refit it after 18 parameters, it does not fit at all. The error, we have lost important predictors in this manner. So we are now sort of forced to look at the model with 32 parameters. And this is the very elaborate model. It's not a very sparse matrix at all. It's the very elaborate model that it contains CZ2, CZ1, and so on. But this is not the very best model. So our approach of proving CECZ has not worked. So there is no real way of so our best model so far has therefore been this one. This has been our best model so far. Up to we have only 9 parameters. Very sparse matrix, 9 parameters. But our best model is not a physically tenable model. Now there is really nothing we can do about this. With the data that we have, this raw data, with the data that we have, this data, this is the best we can do. No matter how unpleasant or that may sound, but there is something else we can do. Let's go back to that data. These data are for a single run. Whenever has process development stopped at one run? Process development does easily 20, 30, 40, 50 runs. So the key is you need not have many runs. Maybe 3 or 4 runs are sufficient. 3 or 4 more runs would be sufficient with different concentrations of catalysts, say. 3 or 4 runs with different concentration of catalysts, different initial concentrations of A, different addition rates of B. 3 or 4 runs would be sufficient to distinguish, to allow the model to distinguish between what is decreasing and what is increasing and what is the correlation between the two. Because if you do that, you allow the model to get that kind of insight. Um, you have a much better model. So let's do one more thing and we'll close. Can you just count how many how many data points we have? We have 44 data points. And how many points of the model do we have? We have 9. So 9 and 44 is a good number, except in this case, this is a plausible model with the data that has been given to the machine. If you want the machine to be able to distinguish between what influences A, what influences B, and so on, we have to give it something more variation, basically. We have to give the machine greater variation, and it will very quickly find out a very plausible model or a set of plausible models from which we pick one that makes good physical sense. Okay, I did not expect to finish this early. I thought this was pretty heavy material. There would be some back and forth. But anyway, I have finished. So if there are questions, I will take them. Otherwise, I will wish you a good day. All right. Are there no questions? I suppose it is not the. Okay, good. Then I will wish you a good day and see you soon. Bye.
Thank you, sir.
Participant, is any question you can ask? No question?
No, okay,
No question.
just look at just remember the name Cindy, Sindy, and a lot of things will come easier later. Thank you and bye.
So there is no question. So I am starting that vote of thank you. Thank you for a session that, thank you, Dr. Vishwanath Dalvi, sir, for a session that didn't just talk about AI, but put it in a place right where it belongs to in service of sound of chemical engineering. Your talk on AI for rapid process development and simulation was there a rare balance of roots and rockets. On one side, you reminded us the power of decentralized ground-up technologies such as solar thermal system, biogas from agriculture waste, where waterless sanitation, and then without blinking, you step into the future, showing how AI can speed up process development and simulation without replacing engineering judgment. Because let's be real, AI is a tool, not a crunch. And you said that clearly and unapologetically. Today's session didn't just add knowledge, it added clarity. It challenged us to think smarter, stay grounded, and build systems that actually matter. Thank you, Dr. Dalvi sir, for your time, your honesty, and for reminding us that the future of chemical engineering is not a flashy. It's thoughtful, inclusive, and deeply responsible. Thank you so much, sir. Now, the next session starts at 2:30.